right, continuing on. So last time we talked about oxidation numbers. Now, that's oxidation numbers within a compound. Let's talk about oxidation numbers within reactions. Now, in many cases, like acid-base chemistry, we're talking about how things change to spot differences. All right. So let's take a look at this reaction, go through it, and identify the oxidation number of every element. Again, think about it in terms of elements. Right? How is this zinc oxidation number? How is this copper's oxidation number? How is this chlorine's oxidation number? And again, the same thing with the starting materials and the products. All right? So let's run through it. Again, pause. For the zinc, oxidation number, it's not +2, it's 0, all right, because it's no charge. If it was a +2 ion, it would be written as charged. What about this copper? Right? This copper is +2, all right, because this is a copper 2 chloride. These chlorides give a charge to this copper. The oxidation number on the chlorines, each is -1, all right, because that's the typical charge on a chlorine ion, and so typical ions that are monoatomic, Cl-, the charge of the atom is the oxidation number. All right, so we have a 0, a +2 copper, and a -1 chlorine. Then we go look at the starting product side, you see exactly the same trends. We see zinc, but it's +2, the chlorine is -1, and the copper is 0. Right? So what's happened is the zinc that was oxidation number 0 has now become zinc +2. And copper, which was +2, now becomes copper 0. Right? This is what we saw. We saw zinc metal disappear and the blue copper leave the solution and become copper metal. So that's our reaction right at the beginning of our talk last module. All right. So these are redox reactions. Right? The zinc is changing oxidation number, the copper is changing oxidation. The chlorine is not changing oxidation number. The chlorine is just there. Right? So, right? Now, if you remember, these are single exchange reactions. Right? This is a single exchange where one element is exchanged for another in a compound. Many of those are redox reactions, and so it's like something to think about when you see them. So the substance that loses electrons is said to be oxidized. All right? We say that the zinc goes from zinc to zinc +2. It has been oxidized from zinc to zinc +2. This is an oxidation reaction, zinc to zinc +2. And in that process, it loses electrons. Those electrons are released. Right? The substance that gains electrons, the one that becomes more negative or lowers the oxidation number, is reduced. Right? You can think of this as changes in oxidation number. The zinc increases its oxidation number. It becomes more positive. Zinc 0 to zinc +2. The copper goes from copper +2. It is then reduced to copper 0. All right. Another way of thinking about this has to do with rust. All right. I like rust. All right. Iron is oxidized by oxygen to make rust. Iron 2 and iron 3. So it increases. Iron goes from iron 0 to iron 3 or iron 2 to make rust. The oxygen oxidizes the iron. All right? So that's the process. Now a mnemonic. A mnemonic is oil rig or Leo says Gur. Oxidation is loss of electrons. Reduction is gain of electrons. or lose electron oxidation, gain electrons reduction. I like Leo Szesger. All right. Now, when we write these, if we think about this, we have the zinc losing electrons. So the zinc loses electrons and the copper gains them. Copper +2. I'm going to leave out the chlorines because they don't change role. Right? And so we can think about the zinc undergoing the reaction, zinc +2 plus Cu, undergoing the reaction, zinc, forming zinc +2 plus 2 electrons. Right? The zinc has lost 2 electrons. The copper, on the other hand, copper +2, has gained 2 electrons. And we can write the little 0 there to denote the oxidation number, just for the sake of clarity for us. All right. So this represents a convenient way to think about the things. If something is losing electrons, it is oxidized. The net result is that it increases oxidation number when it is oxidized. Oxidation number goes up when it is oxidized. Oxidation number goes down when it is reduced. Right? Now we have to be cautious. It's kind of like a negative number. As it gets more negative, 0 to -2 is a reduction, but it's the bigger number, so don't go too crazy with it. Right? Now, in the long history of chemistry screwing with you, the oxidizing agent is sometimes called it is the thing that makes other things oxidize, right? Often called an oxidant. Oxygen is usually a good oxidant. We normally think of oxygen as not, hence the name, all right? When something is oxidized, it is usually oxygen that is doing the oxidation. The result is the oxidizing agent undergoes reduction. The reducing agent is the thing that causes reduction to take place. Right? Like acid-base chemistry, once you identify one species, it's easy to spot the others. So in our example here again, we have zinc. Zinc is being oxidized to zinc +2. So therefore, it is causing the copper to be reduced to copper 0. Right? So the copper +2 is oxidizing the zinc to zinc +2. Right? Oxidants and reductants are always on the starting material. Right? So that makes them easy. Right? And one of the things that takes place in a redox reaction is that a complete redox reaction always has a material being oxidized and a material being reduced. There is always something being oxidized, there is always something being reduced. So let's take a look at this reaction. Oxidation-reduction reactions can take place in the absence of metals. All right? But we can use the same ideas. Let's look at the oxidation numbers for each of these species. All right? You will see that the oxidation number of the carbon, the hydrogen, and this hydrogen are all slightly different. The carbon here, the oxidation number is, I can wait all day. I can hit pause. Each of those carbons has a -2 oxidation number, because hydrogen's typically +2, right? So that's -2. Each of these hydrogens has a +1 oxidation number. And the other hydrogen, the other side of the molecule, each of these carbons is now a -3 oxidation number. So the copper each of those carbons. So if we go through and label our oxidation numbers, we said this is -2, this is +1, this is 0, this is -3, and this is +1. All right. We can see that the carbon has gone from -2 to -3, so therefore this one has been reduced. We can see that the hydrogen, this particular hydrogen, these hydrogens haven't changed, but this particular hydrogen has become oxidized. It's gone from 0 to +1. And so we would say that the hydrogen is causing the C2H4 to undergo reduction. The hydrogen is reducing the C2H4, and in the process it is being oxidized. It's much easier to think of these as, when we have an oxygen. When you have an oxygen there, it's obvious that usually the oxygen is causing other things to be oxidized, but not always, so it's useful. So let's practice this. Okay, let's take a look at this this material. All right, we can see tin has a 0 oxidation number. This copper has a +2 oxidation number. This copper has a 0 oxidation number. This tin has a +2 oxidation. Right? So, what's the oxidant? What is the tin being oxidized or reduced? Again, when we talk about the tin being oxidized or reduced, it starts how it compares to the starting material. Right? So we would say the tin goes from SN0 to SN+2. So this tin is being oxidized, so therefore the copper is being reduced. And we can see that, +2 to 0. And so the copper is the oxidant. This copper is causing the tin to oxidize. Now here's a harder question. How many electrons are exchanged? Well, this tin has to gain, or give up, 2 electrons. And it turns out that the copper also gains 2 electrons. It goes from +2 to 0, so it gains 2 electrons. If we balance all the elements, and we balance all the electrons, and balance the charge, then the entire system is balanced. And that's how you check. Are your atoms balanced? Are your electrons balanced? Are your charges balanced? You can balance any one of these and still be wrong. All 3 of them have to be balanced. And so, let's talk about how we balance a redox reaction, which we will do in the next module. For now, we're just going to talk about spotting what we call a half reaction. A half reaction is a way of simplifying what's going on so that you can look at just oxidation or just reduction. Right? Because we can build up reactions from half reactions. Right? We did this, what we call, we can build up a reaction by putting together the reduction and the oxidation. So let's take a look at a good example of this. So let's take a look at our reaction. If we identify the oxidation numbers, again, first step, start with the oxidation numbers. This one is easy, +2. This one's a little harder, +6. This one is +3, and the +3. Right. Now, let's look at what element is changing. Again, the iron is going from +2 to +3, Fe+2 going to Fe+3. That is our oxidation. And so we think of this as lose electron oxidation. And how many electrons does it lose? It loses 1. Now, the dichromate in this case, has to gain a certain number of electrons for this to be balanced. And we have to look at its oxidation number to figure that out. And so we start with the Cr2O7 minus 2, we can see that the Cr plus 3 is being formed. This chromium is again going from plus 6 to plus 3, and so it gains at least 3 electrons. But here's the thing. There are 2 chromiums here. And so you have a chromium plus 6 and another chromium plus 6. But there's only 1 chromium here, and so there's actually 2 chromiums that you have to worry about. And so the total number of electrons exchange would go from plus 6 to plus 3, plus 6 to plus 3. That's 2 plus 6s going to 2 plus 3s, and so that would represent 6 electrons. Now prove this to yourself, that all of this works out. If there are 6 electrons here, and negative 2 here, and so that would represent the reduction reaction. Chromium plus 2 gaining 6 electrons. Okay. Now, if you remember what I said in the last example, for a redox reaction to be balanced, atoms, electrons, and charge all have to balance. All right? And so that is something that we're going to have to do. But first, go through the process of spotting the half reactions.